Thank you very much for joining this Infoshare related to quantum technology. I am Xavier Janin I am the task leader of the network technology evolution tasks, which is into the work package network technology and services, and with my colleague Piotr Ridlojowski, which is
Hello.
leading this task inside the work package 6, and with the help of Susan Nigel-Jackson that help us to build this Infoshare. We are very happy to welcome you at this Infoshare related to the principle and the possible application of quantum technology in our context. So this Infoshare was realized thanks to the help of the partner relation team of GÉANT. And I would like to recall you that this Infoshare is recorded. So if you want, you can switch off your camera. Therefore, you will not be recorded. And the presentation and the record will be available a few days after this Infoshare. And of course, also all the presentation will be available on the website. So why we would like to speak about quantum, and why specifically we would like to speak about the principle. So you know that quantum is something that really emerging in different technology, improving, for instance, computing, sensors, and different things like this. But quantum things is really different from what we have so far seen. The rules that is in quantum world is completely different from what we see in, I would say, classical world. So there is really a gap between what we knew so far and what is exactly quantum. And so it is why we decided to create a first Infoshare dedicated to the principle. So what is the current situation? There was a first revolutions that enabled a lot of new things thanks to the quantum revolution, such as transistor lasers and different other things. And now we are in the second revolutions, which is about controlling individual quantum system and using the quantum principle like superposition and entanglement to improve different topics like computing, like sensors, and so on. So maybe we reach a point where there will be technical and industrial revolutions. So the question is how to transform this quantum research into an industrial innovation. So I think that you have seen that there is a trend around quantum, and a lot of countries prepare a strategic quantum technology development plan. You can see here the EC, the European Strategic Research Agenda. And one of the purpose of this plan is to create an ecosystem in Europe that allow this quantum revolutions emerging in European industry. Because we need to have the researcher, we need to have some new industries, we need to have also some different partners that cooperate, and so we have to create these ecosystems that allow some industry emerging in Europe. And it is where I think that where our community, research and education, can play a key role for that. So I will now hand over to Piotr, who will chair the rest of this Infoshare.
Thank you, Xavier. So our approach within the network technologies and services development team is to provide some more information regarding the initiatives, and especially for our colleagues at NREN to make them more, let's say, quantum aware, as we proposed, and propose a number of dissemination activities, so like Infoshares like this one, and workshops. We also prepared a white paper that covers a number of topics connected with the quantum technologies, the overview, and for the GÉANT and NREN community, which is available at GÉANT resources webpage. It is already on the chat, so you can download it and get familiar with this paper. And our goal is also to propose training if NRENs and our colleagues are interested in such an option. Other possibility is technology testing. So thanks to the collaboration between NRENs and projects which are run under the European governance, and together with industrial partners, we can present and test the new technologies and within the quantum communication scheme, and of course explore some solutions for the GÉANT network itself. Part of the NRENs are already included in the quantum activities, especially quantum key distribution, so they are partly also engaged in the standardization aspect. So this is also an area where can we contribute. And briefly, our team is consisted of, it's not a large team. We have team, Ivana and Xavier, a team, and Ivana as a package leaders, Xavier as a task leader, and our colleagues Andor, Guy Roberts, Domenico, Peter Kaufmann, Susanne, Rudolf, Josef, Pavel, and myself, and we run the work under the project. Our idea for this Infoshare is to be as much interactive as possible, so we wish to hear your opinions, and you can ask also the questions from the chat. We will have, of course, questions for you, and we wish to have the feedback for the activities. And now we can just quickly ask the first question for the that we prepared on the Mentimeter, and I will hand it to Xavier.
Thank you. I will put on the chat the URL for the Mentimeters, and I will share my screen. So the first question that we ask to you is from, oh, sorry, what's happened? It's not the appropriate one. So sorry for this. We will have to restart. Sorry for that. I don't know why. Result. Okay, sorry for that. I don't know why this doesn't work. So, okay, if you can, the first questions that we would like to, I hope you can see it. The first questions that we would like to ask to you is from which type of organization you are coming from. Of course, what is really important for us activity is to know from which activity you are, because of course it will help us to more identify the topics that is really that we have to target in our activities. Okay, so I think I don't know how many people is connecting currently.
There's 100 people, Xavier.
100 people. Okay, so let's wait a little bit, and after that we could stop. And after that, now that you have the URL, we will have more interesting questions about what do you expect and what is your expectation for the next Infoshare and so on. I think we There is no vote anymore, so I think we have already 60 votes, a little bit more. So maybe you can continue to vote in parallel, but I can hand over to Piotr if you want
Yes.
to restart.
Yes, thank you. So I will follow this from this point. To describe the structure for our today's meeting, just to be quickly, we divided into two sessions, main sessions. We have 2 talks per each sessions, 3 invited talks with our distinguished guests. And as Xavier mentioned, at each of session we'll have an open discussion, and during the discussion we'll also ask further questions on the meter if it's possible. And of course, please ask questions. And without any further delay, I would like to introduce our distinguished first speaker, Professor Eleni Diamanti from the Paris Center of Quantum Computing. She's leading quantum information team, and her main interested and research is connected with quantum cryptography, quantum communication complexity, entangled sources for communication networks, and she's involved in many partners and projects worldwide. So Eleni, please, we are waiting for the presentation. I will not take too much time anymore.
Thank you very much, Piotr. Thank you very much, Xavier. I'm very happy. Thank you for the invitation. I'm extremely happy to be able to share with you some information today. Can you tell me if you can see my screen properly for the presentation?
Yes.
Okay, fantastic. Thank you very much. I'm very excited to be talking to the NREN community, because I really think we can do many things together. There is many things to do in quantum communication and quantum cryptography. So my goal today here is going to give you some main elements related to how the basics, the general aspects of how to treat communication in a quantum world. So we're going to go through the second quantum revolution, some main topics, and then focus mostly on quantum communication with some general ideas, with an opening to the European projects currently in place. So let us start with what has now started being called as the quantum revolution. So I like the plural here, because we can also imagine that there has been already a first quantum revolution, right? So actually we are using quantum theory in pretty much many of the technologies that we're using in our everyday life. And the beginning roughly of quantum theory would start with Planck at the beginning of the previous century, where physicists and engineers and scientists tried to start answering fundamental questions about nature, about the nucleus of an atom. Why do we have thermodynamic anomalies in materials at low temperature? Why is light emitted at discrete colors? So all of the answers to these questions led to the description of quantum theory, where we actually started observing and having a macroscopic manifestation of quantum principles. So this we can actually use this. This took a few decades to be translated into actual devices that nowadays are considered completely mainstream, like the transistor, the hard disk, or the laser that we're using, or even I could add some techniques that are used for medical imaging, etc., that are used currently in our everyday life. So we don't even realize that they are based on this so-called first quantum revolution. So what is happening with the second quantum revolution? So what happens is that just a few decades ago, towards the end of the 20th and now, and the last decades, we have started going further than this macroscopic observation. We can now control single quantum particles, and we have access to the very first quantum algorithm. algorithms. So you see on the left some of the most famous researchers that have contributed and scientists that have contributed to this second quantum revolution. So what does it mean? What is the difference? We're not looking anymore at the macroscopic scale, but we're actually looking at actively manipulating single quantum particles and manipulating the interactions between multiple particles. And for this, we do for concrete applications. So this is the huge difference. This is what differentiates the second quantum revolution from the first one, is that we're actually working at the single quantum particle level, and we are using the properties, as we're going to see, of quantum physics to manipulate information by taking advantage of this control that we have at the not macroscopic, microscopic level, quantum level. So this has led, you have seen this already in a number of quantum technologies that have been developed in the last years in Europe and worldwide. One of the main pillars of technologies is unconditionally secure communication, which is going to be our focus here. There's quantum computing, which leads to a leap in computing power. Quantum simulation is interested in better understanding of complex physical systems. And finally, in quantum metrology and sensing, we're interested in enhancing the measurement precision beyond the classical limit. So these are the so-called pillars that are followed in quantum technologies in Europe and worldwide. And here we're going to focus more on the secure communication aspects that are particularly relevant for telecom optical networks and operators like GÉANT. So let us first start with a few basic notions around quantum information. So Javier mentioned already in his introduction notions like superposition or entanglement. So it's difficult to do this in 15-20 minutes, but I'm going to try to give you some basic notions about how you should understand, we should at least visualize these concepts and how they can be useful, in particular for quantum communication. So what you have to keep in mind is that we're changing information processing paradigm with respect to the classical bit that is dominating all our information processing and communication capacities nowadays. So we're moving from a 0 and 1 bit, which is like the classical unit of information, to a qubit. Okay, a qubit is a quantum bit of information. It can be visualized nicely, I find, in the sphere that you see on the screen, where basically what this tells you is that you can have what is called superposition states. So these brackets that you see here, this notation here, you should always make you think that what is inside this bracket is a physical system. Okay, it's not anymore just a bit of information, but you have to keep in mind, if you stick to the mathematics, that there is so this is the notation that allows you to perform calculations a lot easier, but you should never forget that there are actually physical system behind there. So when we are writing alpha 0 plus beta 1, it basically means that you are positioning your qubit that is used for encoding the information on this sphere, okay, on the outside this area of this sphere. And these alpha and beta are complex numbers. They allow us to position our qubit on this block sphere. And what you should understand is that the alpha square plus beta square equal 1, which basically means that you will always find your qubit, which is in this superposition state, somewhere. Okay, so if you measure it, you have alpha square probability of measuring it in the 0 state and beta square probability of measuring it in the 1 state if you measure it in this 0-1 basis. So this is abstract for the moment. I'll try to give you a little bit more concrete thing of what the 0 and 1s could be in real life in a second. So this is what qubits we use for quantum communication. We use typically photons, okay? So these are single quantum particles, and they can be found in the superposition states. So why do we use photons? They are ideal carriers of quantum information, and particularly for quantum communication. They are robust to ambient noise, and they can be transported over long distances, as you know very well, because we are working with optical systems, and this is why we wouldn't imagine transporting quantum information over very long distances with atoms or ions, for example. It's very normal to transmit them with light. So what are the implications of this encoding of quantum information? As you see here is the figure a bit graphically. What changes with respect to classical systems is we have our alpha 0 plus beta 1 state, this superposition qubit state, where, for example, these arrows here can mean that your photon is in a specific polarization state. So it can be in a vertical or in a horizontal polarization state. And this is particularly interesting, for example, for quantum cryptography. And when you make it pass through a polarization filter, quantum mechanics tells you that your single photon, as we said, has some probability of being projected in one of the two states, these basis states, the vertical or the horizontal. And then you can start imagining more complex situations where you put polarization filters in different angles, and you realize that quantum mechanics at the very single quantum particle level allows you to do something that would not be possible at the classical level. You have, because of this translation of probabilities, because everything is probabilistic, you end up having non-zero probabilities of a photon coming out under certain, of course, circumstances. So you can play with these polarization filters and see that this is what happens when quantum superposition is used. So this is one of the basic elements, one of the basic notions behind quantum communication advantage. The second one is more difficult, is extremely fundamental, is more difficult to explain, and it's linked to entanglement and non-local correlations. So what does this mean? So basically, let's think about it that way. When we work in classical physics, there is no actually random processes in classical physics, okay? Everything that happens, for example, we have the example of a box here where we have the movement of particles, and it may apparently look random, but this randomness comes from ignorance in the classical world. There is always, if we know all the dynamics, if we can write down the dynamics of what's happening in a system, we can always predict the exact path of all the particles. So this led to this paradox, this apparent randomness in classical physics, which is actually not correct, led to the so-called Einstein-Podolsky-Rosen paradox, where they said, oh, well, we think that there is true randomness in quantum theory, but is this correct? Shouldn't it be the case that, in fact, there are some what are called local hidden values, something attached to these photons that would explain the randomness? It means that we wouldn't have a complete physical description of our system, and if we had, it would explain everything that is happening in quantum mechanics. But actually, this is not correct. So when you get a pair of so-called entangled particles, okay, so these are two photons that are in a state intertwined, okay, their quantum state is really truly generated in a condition that you cannot actually tell them apart in any way. And I guess Sebastian in his talk right afterwards will give you examples of how this entangled photon can be used in practice for quantum cryptography. So what is important to remember here is then we can make measurements even when these photons are really far apart with different polarization filters, remember when we talked about, and by correlating these measurement outcomes, we realize that there is true non-locality in quantum mechanics, non-locality and randomness in these quantum correlations that we find when we do this test. So this inherent randomness and this non-locality that are a signature of the quantumness of a system are one of the most important and basic characteristics that lead to a quantum advantage in all quantum technologies, including in quantum communication. The third property that I'm not going to go through here is a no-cloning theorem that states that it is impossible to clone, to reproduce an unknown quantum state without creating an error. Okay, so this is extremely important. I guess you understand for cryptography, it is impossible to take an unknown quantum state and just reproduce it. So all of this comes together and brings us to the field. So I remind you, entanglement, non-locality, superposition, and no-cloning. They come together and they are the fundamental quantum principles that can lead to what we can show with quantum communication networks. So let's go a little bit further and discuss a little bit more detail what I mean by quantum communication networks that you will hear a lot in this type of devices. So my vision, let's say, of quantum communication network is a network with all these users here, where there are devices that can range from very simple photonic devices that can do very simple actions like measure or detect, measure or generate quantum states, or you can go through a quantum sensor, a small quantum device, or up to a full-scale quantum computer. And you want to connect all these processors and these devices for applications. So how do you do this? You encode, as we said, your properties in quantum states of light. You propagate light into optical fibers or free space channels, and you compute, you treat the information with processes and memories in the nodes of the quantum network. And one of the things that you would be interested in is proving security, enhancing the security of your system, given that you will have untrusted users or devices and nodes. And of course, you would want to use optimally your communication resources. From a communication point of view, this is what matters. Okay, we're not talking about computing here. We care about what you can do with such networks. So you want to prove a quantum advantage in this respect. So there is a roadmap that has been put forward for such quantum communication networks, the so-called quantum internet roadmap, where you should go in this graph from the very bottom to the very up, where you see on the left what are the type of quantum networks that we can have, which, as you go up, increases more and more in complexity. You start with a network where you can only have separate nodes, send and receive quantum states, and that's it, okay? And then you just propagate them in your quantum network. Or then afterwards, you can have entanglement, and then you can add storage with quantum memories, and then you can even start doing error-corrected quantum computing, some very advanced things. From a physical point of view. And all of this means that you can increase the complexity of the functionalities that you can access with such networks. Okay, you start from the most basic cryptographic primitive, for example, for which we know how to show a quantum advantage, like quantum key distribution, and then you go to tougher, more and more advanced protocols that will give rise to more and more interesting, if I can call it like this, applications. So let's start with the bottom, because this is what we know how to do today. And let's explain a bit quantum key distribution. So what does quantum key distribution does? It is there for securing network links. We're not going to have the time to go through all the cryptography aspects of why QKD is interesting. You should just keep in mind that modern cryptographic algorithms have to make necessarily assumptions on the computational power of an eavesdropper, okay? So if you want to exchange a secret message today over the internet, for example, when you pay with your credit card to buy a plane ticket, well, that used to be the case anyway, something. So you will need to perform a cryptographic algorithm, and so for this there are all sorts of different protocols that are developed, like symmetric, asymmetric, post-quantum. We're not going to go into the details, but there is always assumptions on the computational power. So if a quantum computer comes ahead, or other advances in mathematical algorithms, it means that some of these algorithms become vulnerable, and some of them are the ones that are really very much used in today's communications. And this is why it's interesting to find the cryptographic solutions. This is where quantum key distribution comes into the place and promises a future-proof, information theoretically secure solution. What you want to do, secure message exchange between two trusted parties. Okay, so this is important to clarify exactly the task that is performed by QKD. So in this language, you have an Alice, your emitter, you have Bob, your receiver, you have Eve, the eavesdropper. They share a quantum channel and a classical authenticated channel. And the very basic idea is, because of the fundamental principles of quantum physics that we just discussed, okay, the no cloning, superposition, and entanglement principle, depending on the protocol, you will be sure that whatever information Eve tries to access, to have from Alice, from what Alice sends to Bob, from intervening in the quantum channel, which can be an optical fiber, for example, then this will lead to errors, and the eavesdropping will be detected, and the two legitimate parties will be able to extract a secret key. So one of the most famous protocols for doing this is the so-called BB84 protocol, the Bennett-Brassard 84 protocol. You will see that it applies exactly the notions that we discussed at the very beginning. Remember when I showed you single photons and polarization filters? This is exactly what BB84 does, okay? So the idea is that Alice is sending 4 different polarization states, so like this, vertical, horizontal, and then diagonal ones. She sends them randomly. She chooses randomly which ones to send. Bob chooses also randomly in which bases to detect with his detectors, and by looking, analyzing their data, Alice and Bob, using the no-cloning theorem and this superposition principle that basically tells you, remember this alpha 0 plus beta 1, that basically tells you that depending on what basis you measure, you may get different results, basically. Then this leads them to this QKD protocol, and again, if an eavesdropper tries to interfere in the communication, perform some measurements, and do stuff with her devices and send them to Bob, it will necessarily lead to errors. Okay, so this is the main point that I want to make here. So this is a prepare and measure protocol where Alice sends photons to Bob, and there is also entanglement-based protocols where there's entangled source and there that is sending the photons to Alice and Bob. So this is, and there the security comes from a non-locality that we just discussed earlier. So there is also a variation that comes in QKD protocols that is more linked to practical considerations. So up till now have said that you can encode quantum information in states of single particles of light or entangled particles of light. I haven't said in which properties. I talked a lot about polarization because it's easier to visualize, but there are other properties that one can use like phase or time arrival, and there is also a whole field in QKD that is using continuous variables. This is more inspired by quantum optics, where you encode your information in electromagnetic field quadrature. So you can see it like this. Instead of single photons, you have your little wave here, the coherent state. You modulate the light here, and then you measure it with coherent detectors. And what is interesting here is that these are the detectors that are typically used in coherent optical communication. So this is an advantage with respect to integration into current telecom networks. It's important to understand that there is a huge variety of protocols. There is not a single QKD protocol. This is an extremely rich and diverse field that has developed tremendously in the last years. There is lots of innovation. And now, for example, we had written this review paper with a few of my colleagues 4 years ago, 2016. So we had put back to then what was the state of the art on point-to-point, so just one Alice and one Bob, and prepare and measure, no entanglement, fiber optic QKD. That was a few years ago. So you can see some aspects that are extremely important. For example, until which distance the systems back then could go. You could see that with cryogenic single photon detectors, you could make it back then to 350 kilometers, right? And you can have with, because you have very, very few noise, little noise in your system, so you can measure your quantum signal. And then at smaller distances, are like metropolitan scale distances, you have more results with higher secret key rates. So you see there is necessarily a trade-off between key generation rate and key generation distance, and that the specific conditions of your experiments are particularly important. And what is nice is that there is such rapid innovation in the field that what were there emerging protocols, like you see here, this MDI, I'm not going to explain it, but it means measurement device independent, has now matured in this last years to a definitely a mature protocol, and one of the most one of the biggest contenders for very applicable, especially for very long distances. So it's not a fixed domain, let's say. It keeps advancing. This is almost leading to my conclusion. So I'm just going to mention a few challenges that are currently the community is addressing. The high cost of the system. So there is a lot of work happening on photonic integration for reduced cost and scalable solutions. We are working a lot in network integration so that we manage to operate in almost in a transparent way QKD systems and quantum communication systems within optical telecom networks, so that that this is super important for compatibility, of course, with conventional architectures, but is also crucial for reducing the deployment cost. So I should tell you that this is not always the case, okay? Sometimes we need dark fibers. It is not easy for many QKD systems to use lit fibers and multiplex with other signals, but this is an extremely important topic in the community. It's also important to understand on this aspect that it is not enough, because there is a common misunderstanding on this sometimes, that it is not enough to take an optical telecom protocol and just lower the intensity and say it is quantum. It's a lot more than this, okay? Even for those QKD systems that are closer to coherent optical telecommunication technology, there is lots of subtleties with respect to the security and the practical conditions that make one protocol secure in the quantum regime. Finally, there is one of the big challenges that Piotr also mentioned is the absence of standards and certification. And of course, there is the inherent range limitation that you saw just earlier due to the optical fiber loss. And the solution to this is quantum networks and satellite communication. So why it is important to have practical testbed deployment and do quantum communication infrastructure is because it allows us to test the interoperability between the systems and, of course, network integration aspects and topology, the benchmark using use cases and standardized interfaces. And there is a big work currently going on towards such networks. The most impressive one is the one that is happening in China, that you see here, a very recent publication with a network covering a big terrestrial area in addition to one satellite link, where the satellite link has been used for QKD, teleportation, and other entanglement-based QKD, for example. So this obviously increases the distances that you can take care of. So these are trusted networks in the sense that the network learns the key, and so the information goes out of the quantum regime in every node. In future, even more advanced networks, you would have to have untrusted nodes for end-to-end security, and in that case you need devices like quantum repeaters, okay, and storage, as we said in these stages of the quantum networks that you saw before. So there is a big program in Europe for this so-called EuroQCI to advance towards this type of quantum communication infrastructures, and the pilot project is called OpenQKD. And for example, in the Paris region, we're really focusing on connecting academic and research institutions using the NREN network. So this is one case where an infrastructure like this could be extremely useful for first test-bed deployments of NRN networks. And with this, I would like to thank you very much for your attention.
Thank you, Eleni. It was very interesting. Maybe just to have one quick question from one of our colleagues. Would you agree to the interpretation that an entangled pair, photons, electrons, forms a new particle, a biparticle with a common non-local properties?
A new biparticle. Well, we often refer, for example, to an entangled photon state as a biphoton state, okay? So when we generate, when we use, usually you have to use nonlinear optics to generate these biphoton states, and with appropriate filtering and manipulation, you manage to extract entanglement out of them. So yes, I think mathematically you have to be very careful because you have to treat them. There is a whole quantum, let's say, quantum formalism of how to treat entangled states. So basically you have to consider them, instead of taking this alpha 0 plus beta 1 that we saw before, which was one single particle state, an entangled state has to be seen as a tensor product mathematically of not of 2 qubit states, because then it wouldn't be entangled, but you have to consider states like alpha 0 0 plus beta 1 1, where 0 0 is the tensor products between 0 0 and a tensor. So mathematically these are tensor products. So if you want, you can consider it as a global, I wouldn't call it a new particle, I would call it a quantum state that lives in a bigger Hilbert space than a single qubit. I would call it mathematically, we know how to describe it very well.
Perfect. Thank you, Eleni. So I think we can move with the second presentation. We can ask the other question in the open discussion. Unfortunately, Professor Diamanti has some limited time, but we try to ask. So let's move to our colleague Sebastian Neumann. He's from the Institute for Quantum Optics and Quantum Information in Vienna, and the team interest is sources of entanglement, fiber, and free space-based quantum communication, quantum sensing, effects, and gravity. So thank you again, Sebastian, for joining us, and the floor is yours.
Thank you. So I will share my screen with you. Can you?
Not for now.
It's starting.
It's starting.
Okay, I just got an error message that Zoom was shut down, but it didn't, right?
No. We can see. Thanks, Sebastian.
Okay. Good. Thank you for the introduction. My name is Sebastian Neumann. I'm, as I was already introduced, part of the Rupert Ursing Group at the Institute for Quantum Optics and Quantum Information. We are mainly an experimental group, so I will have the pleasure of telling you about some quantum applications. As a first overview, just a short structure of my talk. One question, can you see my mouse cursor?
Yes.
Yes. Okay, great. So first I will talk a bit about hot topics in quantum physics. One is quantum simulation, quantum sensing, also of course quantum computing. And then I will put a spotlight on quantum communication because that's actually the area I work in. And I will tell you something about QKD, quantum key distribution with entangled photons, how you can implement quantum communication networks, and also how you can implement long distance fiber connections in the framework of CAPITAL. In my case, CAPITAL is an acronym for Quantum Photonic Intercity Transmission Lattice, and it's a project that's ongoing. I will.
We cannot hear you anymore, Sebastian. Maybe it's only me.
No, it's, I think.
Yeah. So
it's okay now. It's okay now.
Stop. Yeah. I'm having some problems with Zoom, I'm afraid. But so what was the last thing you heard?
You were at Capital.
Okay, so Capital is like a EU project in combination with many other countries where we want to establish quantum fiber connections. I will tell you about this. Okay, so let's start. Quantum simulations can, for example, be used to simulate systems that would be too complex to simulate with a classical computer. It's very closely related to quantum computing, but it focuses very strongly on one specific problem. For example, here I'm showing you pictures from a group at the University of Vienna, not my institute, but very close, and they're using quantum states of photons to simulate molecular bonds, which would otherwise be too complex to describe. That's one way of using quantum physics. Here to the right, you have a very famous example, the LIGO, the Laser Interferometer Gravitational Wave Observatory, which won a Nobel Prize for.
Sebastian, I'm afraid we lost you again.
When you speak.
Okay, yeah, now I'm here again, right? Sorry, I get this error message. Wait, I will try something, sorry.
So can you hear me now?
Yes.
Yes, okay. That was my headset, I think. Okay, sorry. So the LIGO to the right won a Nobel Prize for the detection of gravitational waves. And they are using actually quantum states of light, so-called squeezed states, which can be used to increase the precision of one of your measurement parameters while sacrificing precision in another one. And with this, they were able to measure length scale changes in the order of 1/10,000th of a proton diameter. Another sensing application, which is from our group actually, is what I call torturing a source of entangled photons, because we've done literally anything to it which we could imagine. we put it in a drop tower and where it fell on mattresses, so we could see it behaves in zero gravity or close to zero gravity. We put it in a centrifuge and subjected it to 30 g of acceleration, so 30 times normal Earth acceleration. And it showed that entanglement is actually very robust. So not only our experiment itself, but also the photons we created, there was no degradation of entanglement shown. And another application of the same source, I always like to show this picture because you can see the orange thing here. This is actually a part of a concrete mixer which a colleague of mine bought in a convenience store. So what we did here was we simulated a gyroscope, which is used, for example, in airplanes, which measures the rotational speed of a system. And you can see here on the top right, there's a graph which shows the precision of a classical gyroscope. And below, we could enhance this by a factor of 2 by using more than one photon in an entangled photon state, a so-called noon state with 2 or more entangled photons. And of course, another big hot topic is quantum computing. So I really like this picture because it shows how complex these systems still are at the moment. This is a boson sampling experiment by Chan Wei-Pan's group. It's very recent, published it in December. And there they showed a speed up of a certain problem with quantum with a quantum scheme that improved in comparison to a supercomputer by many orders of magnitude. So the sample time for this graph in the quantum case was 200 seconds, and a supercomputer was estimated to would have taken 600 million years. I mean, this sounds amazing, but I have to be honest, this is a very, very specific problem. So this scheme was built to solve this one problem and essentially nothing else. In this specific case, you can have a very, very high speed up already. However, what you would need to advance to real quantum computing schemes and algorithms would be universal quantum computers, which this, although it's very impressive, is not yet. If you had such a universal quantum computer, this would be a danger for asymmetric encryption protocols such as RSA, which is used right now. Here on the left, you can see a graph where the security issues of such RSA encryption schemes are shown. So on the x-axis, there's the length of your RSA key, which is by recommendation 2048 right now by NIST. And if you would have a normal, like a classical computer, the computing time to prime number factorize this is asymptotically nearing this key and would take longer than the lifetime of the universe to calculate it. However, if you think of quantum algorithms, which are the not so steep lines here, you could actually prime number factorize these values much, much faster. I mean, in a first implementation, which would be probably the first one to be implemented, would still take thousands of years. But if you take the fastest one, even if you increase your key length a lot, you would still be well under 1 hour for cracking it. So this really is a problem for RSA encryption protocols. And however, so this has not been realized yet. And on the right, I like there's a funny graph. So of course you can see the interpolation isn't too precise because there haven't been so many experiments yet. But it's something like a Moore's law for qubits. Qubits you need to compute with in a quantum computer, and there's an optimistic and a pessimistic assumption. But you could say that, like by the end of the next decade, you will definitely have quite big systems of qubits which you can use for computation. But I mean, of course, please don't sue me if this doesn't happen. It's still a very rough interpolation. Okay, so I've shown you how quantum computing can actually be a problem for encryption. And now I will come to the solution to this. So quantum physics kind of is the problem and the solution at the same time. And I'm more concerned with the solution here, so with quantum communication that can give back the security to messages, so to say. I will tell you about BBM92. That's a protocol very similar to the one that Eleni has already explained to you. I'm explaining this because this is the technology we are using for our experiments. It's also the technology for the burst capital connections I will tell you about. And the main difference is that it's entanglement based other than BB84. So you have two channels and the source of entangled photons is in the middle. It's conceptually similar to BB84. So if you look at this is a scheme. This picture is very similar to the one that Eleni has shown. You have to the left Alice, who encodes quantum states of light on the photons, so polarization states, and then Bob measures randomly. And what we do is that we don't have one sender and one receiver. We have two receivers. Alice and Bob perform the same thing. They measure in two different bases. And in the middle, there's an entangled source that sends photons to the two of them. Here you can compare. And the applications are, as I said, for example, quantum networks and long-distance fiber QKD. But before I come to these actual applications, I will show you a very important concept in this BBM92 QKD, and that is entanglement is something like correlated randomness, which is something that classically you cannot really think of, because imagine you have this entangled state and you send two photons and measure them with beam splitters. And depending on their polarization, they are either transmitted or reflected. And I made this euro coin here to emphasize the fact that this is a random process if you just look at one system individually. But if you look at both of them, you will always only get perfect correlations and never the other way around. So although it's random, it's correlated as well. They will always show the same. And that can be now used for creating a key. So you essentially just record all these euro coins with zeros and one. And this is then a one-time pad, which you can use once, add it to your message, and it is absolutely secure because no one could have intercepted it. Or this is prevented by the no cloning theorem that Ellen. Okay, so this just for the concept. Now a bit more practical. This is the source that's currently in my lab. This creates these entangled photons. It's a so-called type 0 source at 1550 nanometer at telecom wavelength. Type 0 meaning that the spectrum it covers is rather broad, so which is very useful because you can use this to multiplex over different ITU grid channels, different VDM channels. And it has a brightness of around 4 times 10 to the 6, so around 4 megahertz per milliwatt. So per milliwatt power of the laser I send in. So if I send more power in, I can increase this value a lot, actually. And the error rate in this case is less than 1%, which is very good for sources like this. If you come from telecom, you'll probably think 0.5% is insanely high, and you cannot really work with this. However, this is only half of the story, because the final key will have only like a bound of, I think, 10 to the minus 9 or something wrong bits in it, because you have to perform error correction protocols anyways if you perform QKD. So 0.5% is totally fine. Here you can see a picture of this spectrum that the source produces. Please don't be confused by the fact that here I have 810 as an X scale. This is just a spectrum from another source, but the 1551 looks very similar. It's rather broad. And what you can do with this spectrum is now you can use the fact that photons that are created in this source are, if they are entangled, they have the exact same distance from the center of the spectrum. So if I look at this channel, it will have its entangled partner photons in this one. You can cut out wavelength channels of this broad spectrum, which are entangled. And this is done by the by normal telecom equipment, which you just order online for, I don't know, 50 to 100 euros with channel spacings defined by the International Telecommunication Union. Here you can see that these channels, the ones with the same color in this table, are the ones that carry entangled photons. So if you select channel 33 and send it to one partner, to Alice, then you have to send channel 35 to the other one, Bob. And so you can do this with many, many channels, but by using just one source. And this is especially useful if you want to perform a network experiment. This is an experiment that was published last year and carried out 2 years ago. I was also participating. You can see on the top left that you have this spectrum of the source, and you cut out these entangled channels, and then you distribute them with a rather elaborate system using VDMs and 50-50 beam splitters, 50-50 fiber beam splitters, and distribute them to 8 users. And as you can see here on the top, really every user has a connection with every other user. That's very, very useful because you need no trusted nodes at all for this network. So every user can be sure that nobody is intercepting his or her communication with anybody else. Actually, this is already one upscale of an earlier experiment because this is scalable to many, many more users. This is the 8-user case. The first publication was with 4-user case. So we are trying to work on increasing the number of participants here. And here just one quick graph where I can show you that the secure key rate, so actually this is also proof that the correlations that are observed are quantum mechanical. They stay above 0 for all of the users over a very long time scale. So here you see 60 times 10 to the 3 seconds. The rates are very different because there was different equipment used. We had different fiber channels, so we really wanted to test several possible situations. Okay, so this was a network experiment with rather short length scales. So here you can see the longest fiber link was 12.5 kilometers, but you can also use fibers for long distance communication. And this is what the Capital project is about, which I'm currently concerned with. This is a map of fiber connections that we have investigated, which could in principle be used for this. Excuse me. The yellow lines are the ones where we're already in the implementation phase. So these fibers can be used by us for our quantum experiments. And the first step will be to establish a connection between these cities. So Ikoki and Vienna will have the source. To the left, it will go to St. Pölten, and to the east, it will go to Bratislava. And this looks like this. So here I want to please.
Sebastian, you have 5 minutes left.
5 minutes, yes.
Thank you.
Yeah, thanks. Here you can see that to the left, you have this 125 kilometer link to St. Pölten, right to Bratislava, and you can establish a secure key between all 3 of these cities. Maybe especially Vienna and Bratislava is probably from a commercial point of view a bit more interesting than St. Pölten, which probably none of you has ever heard of, but they have a very nice town hall. So this is like a proof of principle experiment, but of course we will try to establish many more connections in the future. Just a few technical details about this. So the polarization stability that is needed on these fibers has to be good enough not to mess with our polarization state, which is the state that we encode our qubits in. And we've done some preliminary measurements over 300 kilometers where you can see that the fidelity is over 99% in 50% of cases over 24 hours. So compensation every hour is absolutely sufficient. We have an optimized scheme to do that, which will be implemented. Then another thing is, since we have comparably broad pulses, since we really use the full 100 gigahertz of the VDM channel, not just a part of it like you would with a laser, dispersion actually becomes a problem. So you have around for a 200 gigahertz channel, actually you have around 20 picoseconds per kilometer. So that would blow up to 4 nanoseconds in a 200 kilometer link. And this means that your pulse, as it travels along the fiber, actually broadens, and then you have problems with finding the partner photon at the other side, so to say, because you cannot assign perfect timestamps anymore because they smear out in time, and so you cannot unequivocally assign one photon to the other and know that these were actually the partner photons. But there's actually a cool scheme to repair this. This can be repaired by using devices that are also used in classical telecommunication, like fiber break ratings or dispersion compensating fibers. And there's even a quantum advantage in this because you only need one device for 2 channels. If you have your entangled photon source here, you split it up with a VDM into 2 channels. Here we have a fiber spool, which we use to simulate this here, which disperses your pulse. And in the other arm, you can, by introducing equal and opposite dispersion, you can actually reduce the broadness of your peak again. And if you carry this out, you get this nice graph where you can see that if you have a dispersed pulse to the right, you can actually push these together again until you have a very narrow distribution here. This is from a paper that will hopefully soon be published. And as a final slide, I want to show you the expected key rate we want for this connection between St. Pölten and Bratislava, around 250 kilometers. And we expect around 150 bits per second, which is something that our current model has given us. We expect to happen. It doesn't probably sound like a lot, but there's an important thing about QKD. Other than for common internet connections, you do not need your bandwidth always right away, because you can actually store your key and accumulate it until you use it. So since we plan to have this running as a 24/7 operation, you would have 13 Mbit per day. So if you want to carry out secure communication once a day, you have 13 Mbit, and then you have to wait until the next day, for example. And you could always increase this number by multiplexing, which is something that we have not used here in this link-to-link implementation in the first step. Okay, I hope I could give you a short overview and also some in detail description of experiment I'm working in. This is the group I'm working with, and I'd like to thank you very much for your attention, and sorry for the microphone problems. I hope you could all follow my talk. Thank you.
Perfect. Thank you, Sebastian. So now we can move to the let's follow to the open discussion, and we can, if there is a quick discussion to either Eleni or Sebastian, please do ask these questions.
Well, is there any question for the speakers, because we don't have any time to do?
Yes.
So
maybe I can try. Hi, I see one question from Mikhail, so maybe we can try to answer that one. So
yes,
Mikhail is asking, most of the consumer internet use is now wireless. What are the prospects of getting QKD to your mobile phone or laptop, or is QKD expected to be used only between data centers even in the long term? I guess, I mean, Sebastian, I guess he can say his opinion, but I would say these are two separate questions. For me, so for the moment, optical links are the ones that have that show the most promising performance for QKD. So there has been some work on the RF and other type of things. They are not very conclusive. So getting wireless QKD is not something obvious at the moment. But optical links are more. So this is the second part of the question. However, is definitely more optimistic. So optical links are used more and more in data centers. So actually, the use case of using QKD for securing connections in data centers is one of the most important ones. So there, I can see definitely a future for QKD.
Yes. Just if I may add, of course, it is very hard to connect your phone to QKD, but there's even progress made in that direction. So there was recently a paper by, I think it was a Chinese group, who really managed to send entangled photons
with drones.
With drones and with high precision into single mode fibers, which is insane.
Yes, that was cool.
Yeah. So as of now, it looks very difficult, but there's still progress in that direction.
Maybe I can answer the question from Peter on CVQKD. So Peter is asking, hi, Eleni, Sebastian, entanglement can be used in DVQKD. Is it also used in CVQKD? So the CVQKD systems that I showed, for example, I mean, the most basic ones are not using entanglement, are mostly used using coherent, weak coherent states. I mean, yes, encoding in coherent states, but CV entanglement definitely exists. Even QKD based on continuous variable entanglement has been also shown, so it definitely exists. It's more it's more assumed to be helpful for computing rather than for communication, because of the a little bit, it treats a little bit worse with respect to discrete variable, the losses. So it is more vulnerable, let's say. It's less resistant to losses when you get CV entangled states. So, but it's definitely, technically, it's definitely possible, and it has been shown.
There was one question directed to me. I think, how do you make the entangled photons with the two different energies? So this is actually a process called SPDC, spontaneous parametric down conversion, which covers a rather broad spectrum depending on what crystal you're using. But if you mean how you can have entanglement, although you have two different wavelengths, this is something that can be solved with so-called Sagnac loop, where you can have two photons becoming indistinguishable on a beam splitter because they have two different propagation paths when they hit the crystal. So you cannot distinguish if a photon was red and went one direction, or if it was blue and took the other, for example. I'm not sure if this answers the question. There was Richard Hughes Jones.
Perfect. Thank you, Sebastian and Eleni, for the question. I think we can move now for the break. We will have some Menti questions, but we will do them at the end of the second open discussion. So we could have a quick break till 14:15. So
14:10.
Thank you.
14:10. Thank you. Thank you. So let's welcome our distinguished colleague Tommaso Calarco, who is a professor at Institute of Theoretical Physics, University of Cologne, and director of the Institute for Quantum Control of the Peter Grumber Institute. And professor is also responsible for the Quantum Flagship initiative, and he will tell us a few words regarding the program, the goals, which is, I think, important for our community also. So, Professor, thank you for your time, and the floor is yours.
Thank you very much for your invitation. Apologies that I wear today this monkey suit. Normally, I do not wear a jacket or a tie. I dress like normal people, but today I have some meetings which they are going on uninterruptedly, so that I do not have time to change. So please accept my apology for this little bit ridiculous attire which I have today. And also please accept my apology, but this is not my fault. Of course, this is a joke or half a joke. Not my fault for reusing a presentation which I have given a few months ago in the Swiss Quantum Day. The reason is that I have been asked by Dr. Rychowski to do that. So he said, oh, I liked your presentation. I think it would be well suited for our context. And so, of course, I trusted completely his advice, and I am using these slides, which provide, as was announced, a general introduction about what we are doing in the flagship. So,
exactly.
Very good. So, well, okay, so we can skip the animations and we can go straight to the point in which we want to explain what we are doing in the quantum technology flagship and where we are at this stage. And at the end, I will have also, there are a couple of news which were not yet known when we had this presentation at the Swiss Quantum Day, which I am, of course, very happy to update you. And of course, everybody is very excited, especially there in France, for the big announcement of the 1 billion, which President Macron will make tomorrow. So we are going to have more money flowing into quantum technologies. And so it is a very right moment to start discussing these aspects in terms of how to connect getting information and sharing information on how to connect the different initiatives that we have. So, what are quantum technologies? So, of course, this is very well known to most of you, but it is just to set the stage in the sense that, you know, the way we define quantum technologies in the context of the flagship is broad, but at the same time well-focused. In the sense that we distinguish the first quantum revolution, in which, you know, for instance, now I'm using the quantum devices because electronics and internet communication is made possible only by the fact that we are mastering the laws of quantum mechanics. However, of course, this is not the quantum technologies we are talking about today, because what we call the second quantum revolution is about engineering properties of individual quantum systems. So we are speaking about individual photons, individual electrons, individual atoms, individual molecules, individual degrees of freedom in superconducting circuits, for instance. And this is, you know, quantum technologies are about building on those features in order to enhance the capacity, the speed, the sensitivity of information processing devices. And the one important point is, of course, this comes from research, but the idea is it goes out of the lab into the market in order to bring benefits to society. So there is a research part and there is an implementation part in terms of maybe infrastructure, which I will describe in a moment. So also, I have seen in the program, and I was here for part of the preceding talks, I've seen that, for instance, you have addressed aspects of quantum communication. There are a broad spectrum of applications in quantum technologies. One is about high precision measurements, so ultra precise clocks, which, for instance, are relevant for, you know, like time stamping and standards, as well as for navigation systems and coordination of complex systems like smart energy grids. There are, in the context of quantum measurements, also other aspects of sensing, which can be useful, for instance, for medical imaging. And let's think, for instance, to you know, color centers in diamonds, which can be used as magnetometers to enhance the performance of medical imaging devices. And of course, quantum key distribution is an aspect which has been just discussed, and it is about secure communications. Quantum computing is very much on top of the agenda of many governments, like as we speak. So in a few hours, actually, not only tomorrow, Mr. Macron will announce the 1 billion for France, but tonight, Chancellor Merkel will decide about the 2 billions for Germany for quantum technologies. And one of the main motivations in this context is indeed quantum computing. And then, of course, beyond the quantum measurement aspects that I mentioned before, there are other important applications of sensors. One very important point, especially for France, is that, I mean, in France, there is one of the most prominent startups, the company Nuquance, which is commercializing quantum, most prominent in the context of quantum sensing. They are commercializing a gravimeter, which is transportable. It is not really something which you put in your pocket. You need a vehicle to transport it around, but it is very efficient and much more practical than other counterparts not based on quantum effects. And of course, there are many other startups in France. Just one important one I'd like to mention. I will mention it again in the context of the European Infrastructure for Quantum Computing and Simulation, EuroQCS, is the company Pascal. I will come back to that afterwards. And this is indeed connected to quantum simulation, which is one particular field of application of quantum computers, in the sense that you can use a quantum machine which has perhaps not full control and you cannot do any universal circuit, but you can reproduce the behavior of other quantum systems in a way which enables you to make calculations which are not possible with conventional, classical supercomputers. So all of this comes together in the flagship, which started 2 years ago. Here is a little video of our kickoff meeting 2 years ago in Vienna. The idea is long-term, 10 years, large-scale research initiative. I will give a couple of details on that. And the idea is, as I said before, we want to transition from the lab to the market. And this should really be a collective initiative, because no individual country, no individual university, no individual research institution, no individual company can do it alone. Yesterday, we had an information meeting in which Google was explaining to several European stakeholders. I know that some of you have been attending. I mean, what they are doing now, and their punchline was, this is not a race of one country, one company against another country, another company. It's a race between mankind and nature, and perhaps it's humankind together with nature. So this is really something which is very cooperative, and I'd like to underscore this dimension, which is essential to reach those goals, which is one is we start from an excellent, outstanding leadership and excellence on the scientific side in quantum. And, this is something we want to consolidate and to expand further. And the reason is because we do not yet so much industry involvement. This is going to be a hot topic also in the discussion today with Chancellor Merkel, and I know it is also a hot topic in the discussion in France. There is not yet such a strong involvement of industry in Europe as we have in the US, for instance. Yeah? So this is what we want to kickstart and create the conditions for a lot of industrial investment there, and in order to have Europe as a leader in the future landscape of quantum industry. And we also want to be able to, in this way, attract investment, attract talent, attract resources and business to Europe. So those are the goals of the flagship, which is articulated, as I said before, into something which started 2 years ago, in October 2018, slightly more than 2 years ago. There are 2,000 plus scientists working in the current project. In the first round of the project, those are 3 years projects. The whole initiative is slated to last for 10 years. And the first amount of money which was invested was 150 millions for 3 years, so 50 millions a year, which would amount, so the original plan was this 1 billion euros over 10 years would be half paid by member states and half contributed by the Commission, which would be 50 millions a year by the Commission and the same from member states. Now, if we look at these numbers, like, in Germany, 2 billions in 4 years, in France, 1 billion in 5 years, and other countries as well, we are already much beyond that from the side of member states, but also the Commission. This is the good news that we got over Christmas. So in the trialogue, so the negotiation between Parliament, Council, and the European Commission in December, they came to the conclusion that really they want to have to ramp this up from what was left. It was 500 million minus 150 millions would have been, again, the 50 millions a year, 350 over the next 7 years of the framework program Horizon Europe. Instead, what they are going to do is they are going to triple this, because the goal is to have an investment over the next 7 years of 1 billion euro fresh money from the European Commission. So what we have in the first stage is this 3 years project. Those are 20 projects. I will give a little bit of details on that in the different areas. There are 140 proposals which have been submitted. So the success rate was not negligible, but also not very high. But one important point that we kept, also in comparison with other flagships, was that we wanted this to be and remain open, in the sense that it's a competition. So after 3 years, there are new calls, and the strong actors will compete to get the next round of projects. This is important to keep, not just a closed club and funding always the same people, but really to keep this dynamical and having the best people engaged and the best actors and the best companies which can make this vision a reality. So from the areas that I said before, we distill essentially 5 application pillars, we call them. This is quantum communication, quantum simulation, quantum sensing and metrology, which are grouped together, quantum computing, as well as, very importantly, quantum basic science, in order to continue to provide fresh ideas. This is not only, it is a lot about engineering and industry, but not only about that, it is also about creating new ideas and keeping also the fundamental side of basic science research in quantum alive in order to provide future developments. So you see that projects are quite well distributed in these pillars. I will give a few details on that in a moment. In the quantum basic science, actually, there are slightly more, 7 projects, because they are more exploratory, maybe smaller projects, which are addressing new ideas and which maybe do not yet require the whole critical mass, for instance, of a big project on quantum computing, but still they require some substantial funding in order to be able to test some novel ideas. So if we now go into those areas, in quantum computing, we see here there are 2 projects, and these 2 projects are about creating a quantum computer with ions and with, in one case, and with superconducting qubits in the other case. To this, we had an addition, which was an additional call, which has been done by the Commission last year, which selected one project of about the same size, about 10 million euros for 3 years, on semiconductor qubits, as well as a new project led by a company, by the French company Atos, about quantum software, with a broad participation from all of Europe. So this was for quantum computing. In communication, we have a little bit more diverse situation. So there are projects specifically like this Q-range on which are dealing with the quantum random number generator as a component for quantum communication devices. There are a couple of projects on continuous variable quantum communication, Civic and Unicorn, and there is also KIA, the Quantum Internet Alliance, which is dealing with perhaps also a little bit more futuristic view of developing quantum repeaters and you know, the research which is needed there to create really at European level a quantum internet. The outcome of this is already coming into actual fruition and infrastructure, and I will tell you a few words afterwards. Now, also on quantum simulation, we have two projects, one based on Rydberg atoms and other atomic systems in double traps. This is PASQUANS, coordinated by Institut d'Optique in Paris-Saclay, and then COMS, coordinated by CNR in Italy, which is about a very dedicated type of quantum simulator for the development of quantum cascade lasers. Remarkably from PASQUANS, of which I am proudly one member. I say proudly because one spin-off of our project, which took place which was born in Paris, is the company Pascal, which recently was awarded a grant by the European Commission, together with a consortium at European level of different actors and supercomputing centers, to provide the first integration, and we'll come back to that at the end, between quantum and classical processors. So then also in the sensing arena, we have several projects which deal with both the clock dimension, which I mentioned before, like IQ clock, to create a portable clock based on quantum technology, and also Asterix, which is dealing with defect centers for different applications, magnetometry in medical imaging and other applications of that particular technology of diamond, essentially, and other material defect centers in such materials. And then there are other projects, again, in the sort of in the direction of the medical application, like metabolics and maximal, addressing some specific features and some specific applications of imaging there with atomic vapor cells on alternative technology, and also with again with color centers for some specific aspect like cardiac imaging. So the basic science is more diverse. There are different ideas on different photonics platforms, different, for instance, microwave processing of ions. Maybe now is not the time to go too much into detail. So this is an overview of the different projects that we have. It's more diverse. This is how it should be to sort of create the basis for the next generation of devices. I would like to say that this is not, sometimes, one objection is, oh, this is just, let the scientists play and go on with their stuff if they are not really up to the job of going in the direction of some real application. But this is not the case. And in fact, one of the several actually startups in the quantum technology arena are coming actually from this project. So it's not like this stuff is decoupled from actual applications, only it is in some cases a little bit more upstream, which we need to keep. It is essential to keep research and also basic research hand in hand with technology development. Otherwise, we are going to have the innovation of tomorrow, but not the one of the day after tomorrow. So that's a little bit the idea here. So this is the whole spectrum that I mentioned before, in which we go from the more fundamental side in Horizon Europe to the left. And here we have also Quantera, which is a consortium of national funding agencies, which is now in its second installment with the 38 funding agencies from 31 member and associated states of the European Union. And I am happy to report that the UK has always been part of this. And now since end of December, we have another Christmas present, which is that the UK is going to be, in the context of the Brexit deal, we got the best that we could get under Brexit conditions, which is that they will be able to participate in the framework program. So from the point of view of projects, they will be there as they were before, like Switzerland and Israel, for instance, which are not members of the European Union, but still they can participate in projects. So this is very great news. This is the, I think, the biggest on world scale, the biggest organization and consortium of funding agencies of international scale, and they are bringing together a series of calls on the fundamental side. Now they added, in the last call, they are adding one dimension which is more applied, just to be better in line with the rest of the flagship. The flagship then is also the research part, but already going more towards applications, which is what I illustrated before, and now is in the end of the spectrum, which is connected to Digital Europe program, the new program, not just for research and innovation, but just for digitalization and infrastructure. Two ideas for infrastructure. One is the quantum communication infrastructure, Euro QCI, and which I will illustrate in the next slide. And another one is the quantum computing and simulation infrastructure, Euro QCS. So let me spend a couple of words on that. So the Euro QCI, here the idea is to integrate quantum crypto into standard communication systems, both terrestrial and space-based. And of course, the applications are the ones which many of you are familiar with, protection of data, clock synchronization, and others in government and other security applications. And the idea is really to lay the groundwork for the quantum internet, and also create via public procurement, so creating really a network across Europe of QKD boxes for the moment, and in the future developing repeaters, which can be the backbone on which we create really the quantum internet. So on this, we also created an industry roadmap recently with the Quantum Industry Consortium, which I will discuss at the end. I think I have time in principle until 2:40, I understand. So still 5-10 minutes, I guess. Yeah.
Yes, exactly.
I think we started a little earlier, so I will try to end in 5 minutes, just to stay in the time which was allocated to me in the beginning. And now, Euro QCS, the quantum computing and simulation infrastructure. The idea here is that you take high-performance computing hardware and you couple to it some quantum coprocessor, which in the beginning will work as a hybrid machine. And this has several directions. One is as a testbed facility for people who are developing quantum hardware to see how they can really implement it in a classical context to enhance the performance of supercomputers. But also, and so this is connected to different hardware platforms, and we are planning to integrate many of them. Of course, a very important dimension is the development of applications. So the software and also involvement of industry for the development of use cases is essential here. And the first pilot call was launched last year by the Commission. It was, since it is more mature, also commercially, the aspect of quantum simulation with this company, Pascal, which I mentioned before, which is commercializing a quantum simulator, which can also be used as a quantum computer. I'd like to underscore that. So it also has in perspective the flexibility to be used as a quantum computer. Now with 100 qubits, and I think the next generation, they are already working towards 200 qubits. So this is, there will be two such machines, one in Paris, one in the Zurich Research Center, where I also work, connected to a European network of other actors like in Spain and supercomputing centers in Italy and others, in order to provide this kind of access and create this kind of backbone in which the whole industrial applications can be developed, and people can really get their hands onto these machines, like it is already happening with the IBM machines in the US, and also with Amazon Bracket Service. So this is the other aspect. One important point is that we want to do it made in Europe to not be dependent on initiatives from outside of Europe. Okay, so the final goal, the whole vision, is to get the quantum internet, you can say. And a quantum internet just means that we bring all these ingredients together. Like today, the internet is, connecting via secure channels, computing machines, and also processing data from sensors in the Internet of Things. And it has a terrestrial and a space dimension. This is essentially the same that we are creating with the Euro QCI and the other infrastructures like Euro QCS at European level. So essentially, the status here is that they are still discussing the work program. So there has not been a big update on that, because the next calls, the budget is going to be defined. But we got a very major push, because, as I said, in December, there was this decision from Parliament, Council, and the Commission to essentially enhance the budget for quantum in the next framework program for Horizon Europe to up to 1 billion. And on top of this, there is the money in digital Europe for the infrastructure. So we are, expecting at least 1.5 billion in this whole invested in this whole spectrum of activities from the European side in the next few years. Well, here I had one slide on the Google so-called quantum supremacy experiment. We know that in the meantime they are not so happy to have used this term supremacy, but this is sort of historic. It has, of course, no political connotation, obviously. And this is the point, which is, as many of you probably know, in which a quantum computer can do something which, for a classical computer, even a supercomputer, will take ages to be performed. It is something which is not of immediate use, not of immediate practical use. It's like the Wright brothers flight, in the sense that, it shows it is possible. In the meantime, also, there was the remarkable result also from China, from Jian Weipan, last month, I think, or very recently anyway, end of last year, in which they showed indeed that they can achieve a comparable result also with photonic qubits, as opposed to, of course, superconducting qubits, which Google is using. And this again underscores that the variety of platforms needs to be investigated, as we are doing, in fact, also within the flagship. So the last important point I want to conclude with is, as I mentioned before, there is an important goal to have industry engaged and involved. So we are also creating a quantum industry consortium. We had, unfortunately, we started this during the pandemic time, so we only could have video conferences, but we already have, well, the second video conference we had was in November. There we had about 350 people registered from a broad spectrum of countries, and from more than 250 companies participating in that case. And so we are now going in the stage of founding this association to represent all the interests of the whole quantum industry in Europe. And here is a list of the work packages which have been established, and you will see that, because I understand that the presentation is going to be uploaded on the website of this event today. And so these are the different activities which we are working on. And of course, a very big encouragement from my side, any companies which are participating today or to which you are networked, certainly, there is an opportunity to get engaged with this. And we are securing some support financially to bootstrap the process from the side of the Forschungszentrum Jülich, my research center, which is kindly agreeing to provide some support in this direction. And we're also trying to find some support also from the European Commission side. We know that Commissioner Breton very personally was waiting for this to happen, because he wants to use this as a launch board, as a springboard to launch a discussion with the top level of important European companies, both in the quantum domain and those which are maybe not yet in the quantum domain, but which could contribute to the second quantum revolution. And with this, I think that, yes, I am finished. And I thank you for your attention.
Thank you, Professor. So we have one question, but it's more general, I would say. So just a short question from my side. Are you able to stay 10 minutes, 10, 15 minutes more, or?
That's non-trivial, because I have another thing which is going on now. I could stay for 5-10 minutes. Yes, sure, as long as it is.
So maybe let's try to answer the questions to see your point of view, and we will continue this in the open discussion. From Ruben, for deploying an actual quantum internet on a European scale, still important progress needs to be made. How, in your view, could NRENs prepare and contribute to the larger goal of building this infrastructure quantum internet?
Well, that's a very, very, very important question. I mentioned before, but I didn't touch upon it in the end of the presentation, that we created a document with an industrial roadmap with the Quantum Industry Consortium, which the Commission asked of us and which we delivered, in order to exactly answer that question, in the sense of, okay, now we have some devices which are not only out of the lab, but some of them are already commercially available. But I mean, doing the deployment, like producing those on such scale, which would enable the possibility of having this quantum internet and creating that and connecting all of that across Europe, is very far from trivial. So it requires industrial capability. and it does require, really a concrete roadmap with concrete milestones. So we have produced this document, and it contains, all the consideration about, how you have to create the supply chain, how you have to deal with to regulation in order for this to be also standardized and adopted at the level of all European member states, as well as not only what we do now, which would be point to point, but how do we make sure that we can get the necessary quantum repeaters to achieve the truly continental scale quantum security. So these are all topics which are very much hot topics which have been discussed. There are a lot of measures which need to be taken and steps which need to be taken. On the research side, we have put this as a priority, or rather I should say the Commission, because it is the Commission which owns the calls, in the work program, in the draft work program, which they are elaborating for the first 2 years of calls in quantum technologies. They are putting substantial budget exactly in this direction. On one end, developing the technology, supply the technology, and on the other hand, creating the sort of engineering capability to deploy it. And at the same time, in the EuroQCI, in the European Quantum Communication Infrastructure, now since almost 1 year or maybe even more, they are meeting with a Sherpa group, which is now working in a confidential way, because those are strategic elements which needed to be addressed with the proper level of confidentiality and security. So this is restricted to EU27 member states, and this is also why the Commission has asked us to not publicize, to not spread or share this industry roadmap that we have created. Unlike all other documents which we have done, which have always been completely open because this is the spirit of our community, in this case it was an explicit request from the Commission to keep it confidential. So this is why I know that some of the people here, which I see in this call, have been involved with that. But this is something that, for understandable reasons, starts being information which our governments would like also in part to protect.
Thank you. As a follow-up, we have from Chris question how in general NREN can engage in the quantum flagship and the QCI. I think we can quickly cover that if you wish, Professor.
Oh yes, absolutely. So engaging for actually every actor, okay, there is a possibility to engage with a quantum flagship just by participating into the calls. So joining consortia which are going to apply for funding, as I said, in the next stage. It is not a closed club. There are now consortia which are working in the first phase of the flagship. Those are published on the Commission's website and also on our portal qt.eu. The first way to engage is just register on the qt.eu portal, so you can get information, newsletter, and get up to date with what is happening. But also there you get information about the current consortia. So once you identify the area which is interesting for you, you can engage with that. And engaging with the EuroQCI is something on the industrial side, is something that we are providing via the Quantum Industry Consortium. So the way to get engaged there would be to for an industry to join one or more of the working groups which we have in the Quantum Industry Consortium QUIC, which are also listed both in my presentation as well as on the web portal qt.eu. The association is going to be established soon in the next few weeks. As soon as we have it, there will be a dedicated website which will explain also ways of engagement in that sense.
Thank you. And also from Peter, what is the situation with other country activities? Close cooperation and concurrence and security with respect to USA, China, Japan, and
yes. So there is a wish from the European Commission. Of course, we as scientists, we cooperate without borders. Science has no borders, and there is a lot of cooperation going on already since many years, and it will go on like that on the scientific level. At the level of programs in terms of the flagship, we have a first coordination action, so a project which is funded by the European Commission to explore possibilities for cooperation on the scientific level, in order to protect some of these security and strategically relevant topics, but on the basic science level, with priority with the 3 countries, which are US, Canada, and Japan, and also investigating and looking into cooperating beyond that. So the first step is that already in this next call, they are planning a cooperation together with Canada, in this case, in the sense that you know, there will be consortia funded from both sides, which should come together and propose collaboration projects, which will be funded in a dedicated way across this channel. We have a comparable level of preparation on the content of possible calls with Japan and with the US, and we are waiting for the budget to become available in Japan. In the US, we were waiting for the administration to change, in the sense that, of course, we had the most openness and the neutrality from the point of view of the European Commission, but I should say that this administration has been behaving in a way, the past administration has been behaving in a way which was a little bit, one could say, protectionistic, yeah? So they have not been very open towards cooperation, and so in a sense they have stopped, you know, really moving forward. Not, of course, the people, neither our colleagues nor the actually responsible officials in the administration, but really from the higher level, the context with the previous administration was not so favorable as to kind of be able to develop a strong dialogue. So we have a basis for a strong dialogue with the US, and we hope that at high level, the new administration will be, you know, willing to really put it into reality.
Thank you, Tommaso, for the question. Do we have some more questions? I think we can conclude, as I don't see any other questions from our community. Thank you.
Thank you very much.
Thanks a lot. Thank you. Bye.
Thank you. Bye.
Thank you, Tommaso, for your time and very good introduction and information.
My pleasure. Thanks. Bye.
So the next speaker will be Piotr. So I will introduce Piotr, but you already know it. Do you want to start sharing your screen? In the
Yes.
meantime, I will make the introduction. So Piotr is the head of the Optical Networking Laboratory, Institute of Bioorganic Chemistry in the Polish Academy of Science of Poznan Supercomputing and Networking Center researcher, and is focusing on the optical data transmission technology, electromagnetic wave theory, and propagation simulations. He is already also highly involved in the European QKD project and the quantum flagships. He is also involved in the Polish National Quantum Technology Laboratory, and is the task leader of our quantum key distributions subtask in GÉANT project WP61. Thank you, Piotr. The floor is yours.
Thank you, Xavier, for the introduction. So my presentation will be very short. It's also, I'm using the slides and from the first meeting of the Quantum Industry Consortium, which was held in June 2020. It was given by colleagues, also Tommaso and other colleagues. We want to emphasize that this mechanism is important. As Tommaso already presented, it is, in my view, also important instrument. We should be aware that this mechanism is available and can be used. Just a quick overview of the colleagues who prepared for this first online meeting. And thanks to Monica, which is running the, let's say, organization part, I was able to share these slides. As Professor Kalarko already explained, there are some large number of registrations to participate in the industry, in the Quantum Industry Consortium under the Quantum Flagship. At the moment, it was 270 and almost from all the countries in Europe. And of course, 80%, most of them are companies, small part academic and public institutions. The idea, I think the motivation and idea for the industry consortium was already well defined by Professor Kalarko, and it is heavy involvement of the colleagues from Forschungszentrum Jülich. And as it was prepared also on the slide by Professor, there's there are separate work packages, and during the preparation, there was a large number of participants who prepared all the elements. And the goal of the industry ball is to industrialize the quantum technologies and to create new market and job opportunities, and focus on the companies and especially the cooperation between the companies and governance and other participants from the industry. And voice of the quantum industry in Europe, and present and promote the interest of the quantum industry as a whole. So it's quite strategic and political element that needs to be done. And the task, or maybe I will skip the governance of this system, because I think it's not immediate at the moment. But as Professor already showed, there are some working groups, governance and structure, which is working group number 1, instantation work group number 2, involvement number 3. This is the work group that I'm involved, and different work packages to analyze market trends and use cases, take care of the intellectual property, discuss education standards, and industry state of the art, strategic industry roadmap, coordination process facilitation, ecosystem and funding. Each of the work packages has separate groups, separate, let's say, meetings, and they draft, as Professor explained, the plan for the activities, and we should see more. So there is, regarding the quick just view regarding the governance, we have the General Assembly, Executive Board, Executive Secretary, and of course each of the work packages. And as I explained, each of the work packages is preparing detailed plan and will simply try to advance its activities and follow later. So thank you. This actually, I wanted to just quickly go through this and start the second open discussion. So is there any question regarding the quantum industry? Maybe if I can answer, I could, but probably I would have to forward the question to the colleagues within the working groups.
Piotr,
Yes.
hello everyone. If I may ask a single question, knowing the NREN landscape in Europe, NREN activities, and also GÉANT, with what we do, what we are, how do you see that we can be involved in this whole initiative? What is your take? Do we enter as partners in this quantum industry consortium, in Quantum Internet Alliance? Do we have a position? Do we have a negotiation position as a whole community there?
It's a very, very good question. I think as Tommaso explained, the first part is to engage in the projects and build the consortium. These projects are, to be honest, if you look at the participants, there is a large number of participants in each of the projects. They are quite large projects. So we should try and find the appropriate place for us for a specific. I think as an NREN community, we have a large user base and large use case base, which is important for the project, because if the system, if the technology needs to be commercialized and put in the market, it needs to have a practical use case and user base and testing experience. So this is the place where we are a perfect fit, I think, and we are already, some of the NRENs were asked to participate in the projects and provide the infrastructure for building the quantum communication testbeds using the existing fiber infrastructure and communication infrastructure, and also establish new use cases. Maybe not new use cases, but try to adapt the existing use cases and services to try to use the advantage of those of the projects. And part of the elements that Raimundas you mentioned, it's answered partly in the white paper that we prepared. So I encourage to read that. And for the QCI, each country that signed the will to participate in the Quantum Communication Infrastructure Initiative needs to prepare its own national program for this topic, for this scheme. And I know that some of the NRENs were already asked to join this, this national initiative and try to contribute for the quantum communication infrastructure within a given country. So on the one hand, we could try to identify and participate in the national projects. And on the other hand, we could try to build international consortium, because at some stage, the quantum, at least communication project, will need a larger testbeds, international testbeds to run the projects. As Sebastian explained, for the Q Capital, it spans several countries, and it will be needed also for the quantum communication infrastructure. So, so this is my view. If you have any comment, Raimundas, for that further.
No, thank you. I think that we have to we have to look at it separately for the longer term.
There is another question from Michael Johansson, which is almost the same. How NREN encouraged to apply for membership? So I don't know if there is something in GÉANT that can coordinate this or not. I don't know. Or it is another question.
I think this is a point for the discussion also, because we have to coordinate, I think, our activities within the NRENs. The questionnaire that we did last year for the NRENs, for the involvement in the quantum technologies, showed that NRENs are interested, but there is a problem with training and overall coordination on the international level, let's say. So if if particular, let's say, NREN is involved somehow in a national project which is somehow connected with quantum technologies on international, I think it is very good to coordinate and try to find connection with the programs, with the activities under GÉANT, under our task activities, since it is always encouraged to streamline and encourage cooperation between the projects. So I think we can, if there are not any other question, I think we can move to the open discussion. And since I think I answered the question for the quantum industry or general view, but maybe now we could further ask our colleagues who participate in the Infoshare to answer some questions regarding activities using the Mentimeter that we prepared. So I would really appreciate if you all could answer those questions that Xavier will now launch and show us the results. And we will go back to the discussion after the Menti.
Okay. Just a minute. I will share my screen.
There will be 6 questions, I think.
Yeah. So the result of the first question was that there is mainly some NRENs. That is. So the next question is about how do you rate the importance of quantum communication and security technologies for your organization or for your community? Regarding this, security is really now become a major importance in France. So we already asked this question 1 year ago, and it was always rated as strategic and important also. I think we are still close to 100, so I will wait a little bit that anybody can answer. Okay, there is no move anymore, so maybe we can. We'll wait 1 minute. Well, yeah, maybe we can go to the next questions then. The next questions.
Thank you for the answers.
Yes, thank you. When do you see your organizations involved in the quantum technology era? So this is a quite important question because it's quite an innovative field. So sometimes in the NREN there was a budget constraint. So it's not easy for the engineers to submit such subject. It has to be agreed by the management, of course. So, wow, there is already a third of the audience that is already involved into quantum. So it's really interesting. And I would like to, there is a list, a email list of our group. So the people who are not aware of what we are doing, I encourage them to drop an email to us. So what we can see is that there is almost 40 people who in 1 year will be involved into this. So there is certainly some requirement regarding technology trainings or test bed or something like this that could help you. So the next questions, next questions is what topics would you like to be covered in the next quantum info shares that we plan to organize? So I don't know if it is about a specific use case. Is it about training? Is it about testbed sharing or testbed already are available? I don't know. There is, for instance, a group, IETF, which is starting to be quite active. So is it about metrology, clock, quantum computing? So it's important to say that quantum key distribution is part of the quantum communication. This is quite interesting. We have 4 topics, or 3, at least quantum communication. QKD, IETF, QRG group, and testbed also is something that is really of interest from our audience. Yes, thank you very much for this input. Migration strategy, theory information. Yeah, great. Thank you very much for this. The next questions is the following. Which area would you like in our working group in WP6 to further studies? And do you see any topics that you would like that we collaborate with you on these topics?
In the meantime, maybe Xavier, I will add this question from Ruben. Does quantum technologies need a separate work package task within GÉANT to coordinate NREN efforts, particularly on a European scale? A very good question. I think it depends how we will engage in the project, because the problem is that there is a lot of activities within the Europe, and in order to track and be, let's say, on time with all the programs, national programs, project activities, ultimately we would need to have a separate group, even just for tracking the activities. And if we wish to engage more in the projects connected with quantum technologies, there is also a problem in which part. As Tommaso explained, there are 4 pillars for the quantum technologies, and probably we'd have to differentiate the groups and people who are working on several aspects of quantum technology. Probably for us, the most important part will be a quantum communication, and maybe maybe quantum computing as to connect the centers. But in the end, I think the team we would need to have a permanent team to track those advancement and technologies that are being developed and tested, because this is not only pure research and development, but a lot of these technologies are being implemented in the equipment and tested also on the commercial scale with the operators and commercial companies. There was last year, there was also in the November very good conference. I would have to check the name. Xavier, I'm not sure if you remember the France conference, BPI.
In Grenoble.
Yeah, Grenoble. And there was a lot of discussion regarding practical implementations and how the companies are involved in the, especially quantum computing, and trying to take advantage of these advancements. And they presented some plans. This conference is on the YouTube, so you can try to view and access those presentations. I think it was a very good event.
So the answer, we can see that there is first topics related to technology. It is about testbed and QKD. There is another topics related more to the NREN involvement, which is more, I would say, management in the project topic related. And after that, there is a subject about standards. So standards, maybe you can take give a few words about standards, Piotr.
Yes, it's a very important aspect. It's in Europe, the standardization for I would say for the quantum key distribution technologies is handled by ETSI. And there is a roadmap for the publication of the ETSI documents standardizing those QKD technologies and aspects. There is already a document who that explains and defines the basic building blocks for the QKD systems. But this year and next, especially next year, there will be several new documents from ETSI that will handle QKD technology and other aspects. There will be, in a few days, there will be a published document from the OpenQKD project that handles, OpenQKD project also has a specific work package focused on standardization of QKD. And all the major institutions, companies that contribute to the standardization of QKD are involved in this project, and we will publish in a few days the document with first standardization, let's say, outcomes and proposals. Not all elements can be published publicly, but the document that we prepared will have basic information and public information that that will give an overview on the standardization of QKD. And the test beds, I agree with the, of course, with the choice, as actually this is the, I think, the most important element that projects focus on the quantum key distribution, quantum communication, but in general, quantum technologies, they need suitable test beds because they know that the technologies work in the lab, since this is an advanced stage, but they need to verify it in the field. So this is the right place, I think, for us to use our capabilities in these terms.
So we will go to the next questions, which is what are the obstacles that prevent you to organize the NREN to work on the QKD? This is where we can try to look at if we can provide, for instance, access to a test bed or training or something like this. And
I think,
yeah.
Fabier,
Please go on, Lars.
You're missing a question about having users, right? I think.
Yes.
for some NRENs, it's, you know, we could do this if there are users asking for it, but I think most of us have more to do than we have time for. So as long as there's no users asking for it, we're probably going to do something else that users are asking for.
Mm-hmm. I understand.
Yeah.
But
Lars, maybe you could ask future Bitcoin users which are in danger with their Bitcoin.
I hear that the most important thing for Bitcoin users is to remember their passwords so they can get their Bitcoin when they realize they're very valuable.
Yes, Xavier.
Yes. I just want to answer that. Obviously, it's more end users. That is, it's not something that will be used by the, I would say, the student directly and so on. It's more for the laboratories that is working on this. We are more here, I think, in a way to help a technology to become become more readiness for productions, like we have done with time and frequency and so on. It's really helping. So I don't expect that there is a lot of users, but if in the meantime your country is very interested by promoting this, it's more like this that you can see it.
And we see that the expertise is highlighted as an obstacle, and Indeed, it is a problem, because even at the quantum flagship discussions, conferences, there is a special group who's working on the education in quantum technologies, because it's, as we saw, it's purely not easy physics. If you want to fully contribute, maybe not contribute, but try to understand it and be an active part, it is not easy. And also quantum flagship recognized that there is lack of expertise and programs in the quantum technologies and quantum engineering, I would say. And several countries and universities launch already special programs to teach that aspects and provide additional training in this area of quantum mechanics at the basic level.
With these last questions, I have finished, so I will leave the floor. Thank you very much for your time. So please go on, Piotr.
Yes, so I wanted to just ask if we have, we have a question from Kostas. Can you share the document for the Q key?
For the QQ technology?
I'm not sure if I understand which document.
QKD technology. It was a typo.
We can share the documents that we prepared. It's not. It's not.
It's already. It was also already sent by Ivana on the chat, or by Tim on the chat.
Yes.
The document about the key distribution. So it's not none of those that I've posted in the chat.
Oh yes, it's more
probably
focused.
something that Piotr mentioned during his talk. Mm. We would be happy to, if just that we need to know which one exactly.
Yeah, let's stay in contact. So since we are tight on time, I think this is all the time we have. Please contact us, ask us further questions if you wish. This is not enough. And let's. I will bring the screen with the. With the next.
Yeah, we would like to make few advertisements of others Infoshares that we will organize. There will be another one related to time and frequency on the 9th of March. We plan also to have a QKD, a quantum key distribution specifically Infoshare on the 17th of March. We organize a workshop on network management and monitoring tools the 24th of March. On the 14th and 15th of April, there is the European Persona User Workshop online. So that was the advertisement moment. Thank you.
Thank you, Xavier. And for the second quantum key distribution Infoshare, we have specialists from the OpenQKD project that will give the theoretical and practical talks. So this will be an entirely external presentation by by the institutions.
Xavier, Piotr here, Artur from PSNC. I have a question because as a result of your question, yes, the most of NREN are interested with the testbeds. And the way to do it, in my opinion, is to check what is the plan regarding European work program, and especially for the QCI. And if you could make some kind of the research where will be some kind of the EU calls for the building of such infrastructure across of the Europe. And I think it will be the good base to discuss in the General Assembly or the GPPC if GÉANT together with NRENs could make some leading role and prepare a proposal to build such infrastructure.
Yeah, thank you, Artur. It's a very good point. I will try to handle that. The problem is only that, as Professor Calarco explained, still a lot of information is confidential under the QCI, but we need to take track of it and indeed try to find a way to establish this testbed infrastructure. Yeah, very good point.
Thank you. Piotr, do you see anything else you would like to know? If no, you can go to the very last slide where there is the email list. If you want to contact us. Thank you. Come back.
Yes.
Down. Yeah, just to once again, after the end of the second session, come back.
The contact is only I have with this.
Yeah. Okay.
Okay.
But there was okay. So if you need to contact us, please use this email, and also you have the list of the member of the team. We can therefore your input will be very, very useful. Piotr,
Yes.
Do you have anything else to add?
Thanks, Javier. Yes, please do contact us if you wish. If you have some questions, proposals, and I think from my side it's fine. I don't want to take much more of your time today. Thank you for large turnout and your kind participation.
So with this, we are done. Thank you very much.
Thank you.
Thank you, Xavier, Piotr, everyone.
Thank you. Goodbye.
Thank you,
Of course,
Thank you.
Thank you. And of course, thank you to all of the colleagues that contribute already to the.
Yeah.
Thank you very much. Bye.
Thank you all. Thank you.
Bye.
Thank you. Bye. Cheers.
Thank you very much, Piotr, for the. You were the great chairman.
Thank you. Goodbye.
Bye.